Welcome to the video lecture series Digital Filter Design and its Application. My name is Dr. Anilesh De, Associate Professor, Department of Electronics and Communication Engineering, Narula Institute of Technology, sharing this subject with one of the renowned professor, Professor Dr. Sholil Kumar Shannan. Professor Dr. Sholil Kumar Shannan, retired professor and head, Department of Electronics and Telecommunication Engineering, Jadavpur University. Presently, Professor Dr. Sholil Kumar Shannan working as a professor, Department of Electronics and Communication Engineering, Narula Institute of Technology. This is lecture 2. In this lecture, I first go for introduction of analog filter design. Analog filter is continuous time system. System processes parameters like cutoff frequency, pass band, stop band, and transition band. Design of analog filter basically means derivation of transfer function Hs. There are many types of analog filter available. Most popular is Butterworth filter. Other filters are Chebyshev filter. It categorizes into Chebyshev 1 and Chebyshev 2. Elliptic filter, Bessel filter, Gaussian filter, optimum L filter, etc. First, I'll go for the analog filter approximation. It is ideal low-pass filter. It passes the frequency till cutoff frequency Fc. After that, it blocks all the frequency as shown in the figure. Now, in this figure, y-axis represented by Hf mod of that and x-axis represented by F. And this is Fc indicates the cutoff frequency. So it passes frequency till cutoff frequency Fc. So from this end to this end is known as a pass band. And from this point to till end it is a stop band, because it is already mentioned that after that it blocks all the frequency as shown in figure. So it passed all the frequency, that's why it is known as a pass band. In here is stop all the frequency, that's why it's known as a stop band. Approximation in ideal characteristics. Now here y-axis represent that H of a mod of that, and x-axis is represented by F. This is pass band frequency, this is cutoff frequency, and this is the stop band frequency. And this distance del F, it is the transition band frequency. It is the from the pass band to stop band, this is the transition band frequency. Now, at the starting point, it is the maximum value, that is the 0 dB, and this is the 3 dB where the cutoff frequency is there. So here it is represented in dB scale. If I represent it in the absolute scale, so we are starting with 1, and rather than the 3 dB, this will be value that 1 by root 2, that is nothing but the 0.707. Now I'll explain everything in detail. Several approximations have been made as shown in the last figure. Fp is pass band H frequency at which the reduction has been started. Fs is stop band H frequency at which filter blocks all the frequencies. Fc lies between the Fp and Fs. Fc 3 dB down to maximum value in the dB scale, and 1 by root 2 of the maximum value of the absolute scale. Del F is the transition frequency from the pass band to stop band. Now we explain the specification of magnitude response of analog low-pass filter. So y-axis is represented by h of j omega mod of that, and x-axis is represented by omega. This is the maximum value started with a 1. In this position, this value is the 1 by root over of 1 plus epsilon square. In this position, it is value the 1 by root 2. In this position, it is value the 1 by root over of 1 plus lambda square. This point is the pass band frequency. This point is the cutoff frequency. This point is the stop band frequency. So this is pass band. This region is located for the stop band, and this portion, the red portion where indicated the red portion, this is nothing but the transition band. Now look at here. We just find it out. There is a, in the practical filter, there is a find the ripple in the pass band as well as the stop band. Pass band ripple is determined by the epsilon, and stop band ripple is determined by the lambda. Now omega p is the pass band frequency in radian, omega is stop band frequency in radians, omega c 3 dB cutoff frequency in radian, epsilon is the parameter specifying allowable pass band, lambda is parameter specifying allowable stop band. So these are the very important parameters, and from the next lecture when you go for the derivation of the transfer function of the Butterworth filter, then we can find it, use this kind of abbreviation and this omega p, omega s, omega c, epsilon, lambda, it everywhere. So please remember this thing. Magnitude response of the Butterworth filter. In this figure, it is represent that it is the order in analog Butterworth filter. Now from here, it is clearly visible that magnitude response of Butterworth filter decreases monotonically as frequency increases from 0 to infinity. Now what will happen? Now here the order of the filter, we can find out the n in increasing in this direction. So at that time, if I take it is the ideal characteristics, and all the points started from this one, and when the n increases, this is coming to the closely coming to the cutoff frequency. So this is the magnitude response of the Butterworth filter. Feature of the Butterworth filter. The magnitude response of Butterworth filter decreases monotonically as frequency omega increases from 0 to infinite. The transition band is more than the Chebyshev filter. The magnitude response of Butterworth filter closely approximates the ideal response as the order n increases. The poles of the Butterworth filter lie on a circle. These are the references. Now this is the end of lecture 2. These are our contact details. You feel free to write us if you have any doubt and query. So this is the end of lecture 2. Meet you in lecture 3. Now if you like, then you please subscribe our YouTube channel.